decades, the moon was seen as a barren, static landscape. But in recent years, China has changed our understanding for good. Equipped with state-of-the-art technology, Chinese rovers and orbiters have given us a closer than ever before look at uncharted lunar terrain. China has also collected samples of the moon's rocks and dust and returned them to Earth for closer examination. What they've discovered, however, is far from ordinary. So much so that experts like deGrasse Tyson have raised the alarm over how China has just found something on the moon that changes everything. This is one story you can't miss. Let's get started. The mystery of the moon and its role in Earth's uniqueness. For centuries, the moon has been a source of wonder, inspiration, and scientific curiosity. It looms large in Earth's night sky, a constant companion whose presence is as ancient as the tides it pulls. Yet, despite the many missions and studies conducted over the past 6 decades, the moon remains an enigma. Well, you see, Earth is, by every measure, an extraordinary planet. Nestled within the habitable zone of the Sun, it is the only known world in the universe teeming with complex life. One of the most overlooked yet critical factors in Earth's uniqueness is the presence of the moon. Unlike any other planet in the inner solar system, Earth boasts a satellite that is unusually large relative to its size. The moon's diameter, 3,474 kilometers, roughly a quarter of Earth's, making it the 5th largest moon in the solar system. It is far larger than the diminutive moons of Mars, Phobos, and Deimos, which measure a mere 22.4 kilometers and 12.4 kilometers in diameter respectively, so small that they could easily fit within the city limits of Chicago. In contrast, the gas giants like Jupiter and Saturn have moons such as Ganymede and Titan that surpass the moon in size, but these planets themselves are colossal, dwarfing Earth by factors of hundreds in mass and volume. Jupiter, for instance, is 318 times Earth's mass, while Saturn is 95 times heavier. The presence of a moon like ours orbiting a relatively small, rocky planet is an anomaly. So far, we have no straightforward explanation, but this may change in the future. Venus, often called Earth's twin due to its similar size and mass, has no moons at all. This absence is not a trivial detail. It has profound implications for planetary dynamics and evolution. Without a moon, Venus lacks the gravitational stabilizing force that Earth's moon provides. Earth's axial tilt, responsible for the predictable cycle of seasons, remains relatively stable thanks to the moon's gravitational pull. Without this stabilizing effect, Earth might wobble wildly over long timescales, leading to chaotic climate swings that could have made the evolution of life far more difficult, if not impossible. Mars, with its tiny, irregular moons likely captured from the asteroid belt, offers a similar story. Lacking a large satellite, Mars has a more variable axial tilt, contributing to its harsh and unpredictable climate. So, why does Earth have such a massive moon, and how did it come to be? The leading theory, known as the giant impact hypothesis, suggests that around 4.5 billion years ago, a Mars-sized object named Theia collided with the young Earth. The colossal impact ejected vast amounts of material into orbit, which eventually coalesced to form the Moon. Evidence supporting this theory includes the isotopic similarities between Earth's and the Moon's rocks, particularly in oxygen isotopes, as confirmed by samples collected during the Apollo missions. However, this theory is not without its problems. The isotopic signatures are so closely matched that some scientists argue it's unlikely the Moon formed from a mix of Earth and Theia. Rather, the Moon appears to be almost entirely derived from Earth's mantle. This discrepancy has led to alternative models, including suggestions that the impact was far more violent than previously thought, or that multiple smaller impacts contributed to the Moon's formation. Adding to the intrigue are the results of more recent lunar exploration efforts. China's Chang'e program, named after the Chinese moon goddess, has been at the forefront of a renewed era of lunar science. Chang'e 4, which landed on the far side of the Moon in 2019, the first mission to do so, has been exploring the South Pole Aitken Basin, one of the largest and oldest impact craters in the solar system. The Chang'e 5 mission, launched in 2020, successfully returned 1.73 kilograms of lunar samples from the Oceanus Procellarum region. Analyses of these samples have revealed unexpected mineral compositions and isotopic ratios. The Moon's gravitational pull governs the tides, which in turn have shaped coastal ecosystems and possibly even played a role in the development of life. Some researchers argue that the tidal pools created by the Moon's pull could have been crucibles for the chemical reactions that gave rise to the first organic molecules. Moreover, the Moon's presence has influenced human civilization in profound ways, from the earliest calendars and agricultural cycles to religious symbolism and artistic inspiration. But so much has to be answered. Was the formation of the Moon a cosmic accident, or is it a necessary component for the emergence of complex life? And could the rarity of such large moons explain why we have yet to find another Earth-like planet in our galaxy? Theories about the Moon's origin. As noted earlier, the giant impact hypothesis, also known as the Big Splash model, suggests the Moon's formation was the result of a cataclysmic collision between the primordial Earth and a rogue Mars-sized protoplanet called Theia. This event is believed to have occurred approximately 4.5 billion years ago, roughly 100 to 200 million years after the solar system began to form. According to this model, Theia's impact with Earth released a tremendous amount of energy, equivalent to billions of nuclear bombs detonating simultaneously, melting and vaporizing both bodies in a planetary scale inferno. The molten material and vaporized rock ejected into space eventually coalesced due to gravity, forming a disk of debris that orbited Earth and gradually accreted into the Moon. This theory not only accounts for the Moon's large size relative to Earth, but also its chemical and isotopic similarity to our planet. Lunar rocks brought back by the Apollo missions played a critical role in shaping this understanding, as they revealed that the Moon's composition, especially its oxygen isotopes, closely matches Earth's mantle. The Apollo program, which spanned 6 missions, Apollo 11, 12, 14, 15, 16, and 17, returned a total of 382 kilograms or 842 pounds of lunar samples from various regions of the Moon. Detailed analysis of these rocks showed that, although the Moon lacks certain volatile elements, it shares key isotopic ratios with Earth. For instance, the oxygen isotope ratios in lunar rocks are virtually identical to those found in terrestrial rocks, suggesting a common origin. This stands in stark contrast to meteorites from other parts of the solar system, such as Mars or the asteroid belt, which exhibit distinctly different isotopic signatures. Moreover, the Moon's lack of an iron core comparable to Earth's further aligns with the impact model, as simulations indicate the Moon would primarily form from the lighter, outer layers of Earth and Theia, while most of the metallic core material would merge into the Earth itself. Supercomputer simulations conducted in the 21st century, including landmark studies by Robin Canup in 2004, and later refinements using improved physics models in the 2010s, have lent further support to the giant impact hypothesis. These models suggest that the energy from the impact would have been sufficient to vaporize large portions of both planets, creating a synestia, a rapidly spinning, donut-shaped mass of vaporized rock that eventually cooled and condensed into the Earth-Moon system. The models also help explain the Moon's orbital dynamics and its relatively small iron core, reinforcing the idea that it formed from Earth's crust and upper mantle material, rather than from an independent body captured by Earth's gravity. However, the theory is not without its challenges. One lingering problem is the isotopic similarity between the Moon and Earth. If Theia came from a different part of the solar system, Its isotopic composition should have been different, leading to a moon with mixed signatures. The fact that the moon's isotopic ratios are nearly identical to Earth's suggests either that Theia had a similar composition, which is statistically unlikely, or that an unusually thorough mixing occurred during the impact. Other theories, though less popular today, have also tried to explain the moon's origin. The fission hypothesis, proposed by George Darwin in 1879, the son of the famous Charles Darwin, suggested that the moon split off from a rapidly spinning molten Earth, possibly from the Pacific Basin. The capture theory posits that the moon formed elsewhere in the solar system and was later gravitationally captured by Earth, but this model struggles to explain the isotopic similarities. The co-accretion model suggests that Earth and the moon formed together as a double system from the same region of the solar nebula, but it fails to account for the moon's small iron core and differences in density and composition. These alternative theories, while intriguing, have largely been set aside in favor of the giant impact hypothesis. Recent missions, such as NASA's Lunar Reconnaissance Orbiter, launched in 2009, and China's Chang'e program, including Chang'e 4's historic 2019 landing on the far side of the moon, continue to gather new data that may help refine or challenge existing theories. Future sample return missions, like NASA's Artemis program and China's Chang'e 6 and 7, are expected to bring back lunar material from previously unexplored regions, such as the moon's south pole, which could shed new light on its formation. So, what has China discovered, and why is the nation obsessed with the moon? China's pioneering lunar exploration. In the last 5 years, China has boldly pushed the boundaries of human knowledge about our celestial neighbor. With an unwavering focus on the far side of the moon, an enigmatic region that had remained untouched and unseen by human eyes, China has invested billions of dollars in developing advanced robotic technologies and pioneering missions that have fundamentally reshaped our understanding of the lunar surface. The far side, permanently hidden from Earth due to the moon's tidal locking, presents a vastly different landscape compared to the familiar near side, and China's Chang'e program has spearheaded efforts to decode its secrets. The Chang'e 4 mission, launched on December 7, 2018, and successfully landed on January 3, 2019, in the Von Karman crater within the South Pole Aitken Basin, marking an unprecedented achievement in space exploration. No other nation had ever landed a spacecraft on the far side, a region long considered a scientific frontier due to its rugged terrain, communication challenges, and the need for sophisticated relay technologies. While the near side is dominated by large, dark basaltic plains known as maria, which were formed by ancient volcanic activity, the far side is mostly covered in highlands composed of light-colored anorthosite rock and heavily cratered by eons of meteorite impacts. This stark difference in terrain, volcanic lowlands on one side and heavily cratered highlands on the other, has long puzzled scientists. The Chang'e 4 mission was designed specifically to explore this mystery, deploying not only the lander but also the Yutu-2 rover, which has since traveled over 1,500 meters across the rugged surface, analyzing rock samples and sending back invaluable data on the composition, mineralogy, and radiation environment of the far side. One of the most remarkable engineering feats of the Chang'e 4 mission was overcoming the communication barrier imposed by the moon itself. Since radio signals cannot travel through the moon's bulk, direct communication between Earth and a spacecraft on the far side is impossible without a relay. China anticipated this challenge by launching the Queqiao relay satellite in May 2018, positioning it at the Earth-Moon L2 Lagrange point, about 65,000 kilometers beyond the Moon, where it maintains a stable orbit and constant line of sight to both the lunar far side and ground stations in China. This strategic placement has enabled continuous data transmission and real-time control of the Chang'e 4 lander and Yutu-2 rover. The data collected by the two has already led to significant scientific breakthroughs. For instance, spectroscopic analysis by U22 has revealed the presence of materials such as olivine and low-calcium pyroxene, suggesting that the lunar mantle may be exposed in certain areas of the South Pole Aitken Basin. This finding supports the hypothesis that the basin was formed by a colossal impact early in the Moon's history, possibly over 4 billion years ago, and that the far side's composition preserves clues to the Moon's primordial crust and mantle. Furthermore, Chang'e 4's Lunar Lander Neutrons and Dosimetry or LND instrument, developed in collaboration with Germany, has provided the first measurements of radiation levels on the far side. It recorded an average daily radiation dose of 1369 microsieverts, about 2.6 times higher than the dose experienced on the International Space Station, emphasizing the need for robust shielding and safety measures for any future crewed missions to the lunar surface. China's lunar program did not stop at Chang'e 4. The Chang'e 5 mission, launched in November 2020, successfully returned 1.73 kilograms of lunar samples from Oceanus Procellarum, marking the first sample return from the Moon since the Soviet Union's Lunar 24 mission in 1976. China also has ambitious plans for future lunar exploration, including the Chang'e 6 mission, which aims to collect samples from the Moon's South Pole, an area of high interest due to the possible presence of water ice and unique geological features. Chang'e 7 and 8, scheduled for later in the decade, are designed to scout potential sites for a long-term research station, with Chang'e 8 expected to test technologies for in-situ resource utilization, such as 3D printing lunar structures using regolith. In parallel, China's National Space Administration, or CNSA, has outlined its long-term vision through the International Lunar Research Station, or ILRS project, a collaborative effort with Russia and potentially other nations, aimed at establishing a permanent robotic presence on the Moon by the 2030s. This vision reflects China's determination to become a dominant force in lunar exploration, not just as a scientific endeavor, but as a strategic investment in the future of humanity. Discoveries on the far side. The Chang'e 4 mission and U22 rover. Launched by China in December 2018, the Chang'e 4 mission was humanity's first successful landing on the far side of the Moon. The mission's focal point was the von Karman crater, an immense 180-kilometer wide impact basin located within the colossal South Pole Aitken Basin, or SPA. To appreciate the scale of this achievement, the von Karman crater alone stretches nearly the length of Cuba, while the SPA itself, spanning 2,500 kilometers in diameter, is a staggering scar on the lunar surface, one of the largest and oldest impact structures in the solar system. Scientists believe the SPA was formed over 4 billion years ago, during the Moon's tumultuous early history, making it an invaluable time capsule that preserves clues about the solar system's violent beginnings. The impact that created the SPA likely punched through the lunar crust and exposed deep layers of the Moon's interior, ejecting material from depths of up to 13 kilometers beneath the surface. For planetary scientists, this region represents an unparalleled window into the Moon's geological past, offering a chance to study not just the crust, but potentially the lunar mantle itself, a goal that no previous mission, including the Apollo program, had managed to accomplish. The Chang'e 4 lander touched down in the von Karman crater on January 3, 2019, and deployed the U22 rover, an agile six-wheeled robot weighing 140 kilograms and equipped with a suite of scientific instruments, including a panoramic camera, a visible and near-infrared imaging spectrometer, or VNIS, and a ground-penetrating radar, or GPR, capable of probing up to 30 meters below the surface. U22, whose name means Jade Rabbit 2 in Chinese mythology, quickly began its slow crawl across the rugged, pockmarked terrain, setting a new endurance record as the longest operating rover on the lunar surface. The rover has traveled over 1,500 meters, far surpassing expectations. Using its VNIS instrument, U-22 analyzed spectral signatures of rocks scattered across the von Karman crater floor. In May 2019, scientists reported that some of these rocks contained a mix of low-calcium pyroxene and olivine, minerals typically associated with the lunar mantle rather than the crust. This finding, published in the journal Nature in May 2019 by lead author Chunlai Li of the Chinese Academy of Sciences, marked the first time that mantle materials had been directly observed on the lunar surface. It was a discovery that eluded the Apollo missions. The implications of U-22's discovery are profound. The presence of mantle rocks on the surface suggests that the impact event that created the South Pole Aitken Basin was powerful enough to excavate material from the Moon's interior, offering a rare opportunity to study the composition and evolution of the lunar mantle without the need for deep drilling. This data has fueled new models of lunar formation, supporting the idea that the Moon underwent a period of global magma ocean crystallization early in its history, followed by differentiation into distinct crust and mantle layers. The confirmation of olivine-rich rocks on the far side also raises questions about the asymmetry between the near and far sides of the Moon. Why does the near side, with its basaltic maria, differ so dramatically from the highland-dominated far side? U-22's findings hint at a more complex geological evolution than previously thought, possibly involving asymmetric heating, tidal interactions with Earth, or variations in impact history across the lunar surface. But wait, there's more. The monolith. In November 2021, during its 36th lunar day, China's U-22 rover, part of the Chang'e 4 mission, captured an image of a peculiar cube-shaped object on the horizon of the Moon's far side. The object appeared approximately 80 meters away, situated within the von Karman crater in the South Pole Aitken Basin. The image, disseminated by Our Space, a Chinese science outreach channel affiliated with the China National Space Administration or CNSA, quickly garnered international attention. Dubbed the Mystery Hut, the object's geometric appearance sparked a flurry of speculation, ranging from natural rock formations to artificial constructs reminiscent of the monolith in Stanley Kubrick's 2001 A Space Odyssey. The initial photograph, taken from a distance, showed a grey, cube-like silhouette contrasting starkly against the lunar landscape. The unusual shape and the lack of immediate context led to widespread curiosity and imaginative theories about its origin. The U-22 mission team adjusted the rover's trajectory to investigate the object more closely. Given the rover's average speed and the challenging terrain, it was estimated that reaching the object would take 2 to 3 lunar days, equivalent to 2 to 3 Earth months. As the rover approached the object, subsequent images revealed that the Mystery Hut was, in fact, a rock. The initial cube-like appearance was a result of the interplay between light, shadow, and the rover's viewing angle. Upon closer inspection, the rock lacked the sharp edges and uniformity that had characterized its distant silhouette. Despite the anticlimactic revelation, the incident highlighted the importance of in situ exploration and the value of ground-level observations in planetary science. The Mystery Hut reminds us of the Moon's capacity to surprise and the necessity of cautious interpretation of remote sensing data. Moreover, the event demonstrated the effectiveness of the Chang'e 4 mission's communication strategy. By engaging the public through platforms like Our Space and sharing real-time updates, CNSA fostered a global conversation about lunar exploration and scientific discovery. The U-22 rover's encounter with the Mystery Hut also emphasized the challenges of operating on the Moon's far side. The rover relies on the Queqiao relay satellite, positioned at the Earth-Moon L2 Lagrange point, to maintain communication with mission control. This setup is essential for transmitting data and receiving commands, given the far side's perpetual orientation away from Earth. The successful navigation and investigation of the object showcased the robustness of China's lunar exploration infrastructure and the capabilities of its autonomous systems. The Mystery Hut episode illustrates the dynamic nature of planetary science, where unexpected findings can prompt a re-evaluation of assumptions and methodologies. It also reflects the iterative process of discovery, where initial observations lead to hypotheses that are tested and refined through continued investigation. The incident serves as a case study of the importance of skepticism, the potential for misinterpretation, and the value of direct exploration in unraveling the moon's many enigmas. Dire consequences. If China controls the moon. In recent years, China's accelerated advancements in space exploration have raised significant concerns among global experts, particularly regarding the potential consequences if China were to establish control over the moon. Gordon G. Chang, a senior fellow at the Gatestone Institute, has been vocal about the strategic implications of China's lunar ambitions. In a 2023 Newsweek opinion piece, Chang emphasized the possibility of China asserting territorial claims on the moon under the guise of scientific research. He warned that such actions could lead to China declaring, "Keep out, we're here, this is our territory," challenging the principles of the 1967 Outer Space Treaty, which prohibits national appropriation of celestial bodies. The strategic importance of the moon extends beyond territorial claims. Richard Fisher of the International Assessment and Strategy Center highlighted that control over lunar resources could enable China to build spacecraft on the moon and develop space-based solar power stations. These capabilities would not only bolster China's space infrastructure, but also provide significant economic and military advantages. Fisher noted that from the moon, China could better surveil cislunar space and potentially station laser or missile systems to target critical American satellites in deep space, posing a direct threat to US national security. But wait, there's more. The possibility of establishing lunar bases has shifted from science fiction to a near-future reality, especially as advancements in space exploration accelerate. The moon's proximity, just 4,400 kilometers from Earth, makes it the most practical target for permanent off-world settlements. Several factors make lunar bases feasible. The moon's low gravity, which is 1/6 of Earth's, its potential resources like helium-3, water ice in permanently shadowed craters, and regolith that can be used for construction. Bases on the moon could serve as launch pads for deeper space missions, such as to Mars or asteroids, and provide critical testing grounds for life support systems, radiation shielding, and long-term habitation technologies. China is actively pursuing a lunar base, with concrete plans already taking shape. Under the International Lunar Research Station, or ILRS program, a joint project with Russia's Roscosmos, China aims to establish a robotic research station by 2035, with a crewed outpost expected in the 2040s. The ILRS would be located near the moon's south pole, an area rich in water ice deposits. The Chang'e program has laid the groundwork, with Chang'e 6 returning lunar samples in 2024, Chang'e 7 slated for a detailed survey of the South Pole by 2026, and Chang'e 8 testing in situ resource utilization by 2028. The Long March 9 heavy-lift rocket, expected in the early 2030s, will enable the large-scale construction of a lunar base. If China beats the US to establishing a permanent lunar presence, the ramifications could be significant. Firstly, it would represent a symbolic victory in the new space race, akin to the Soviet Union's early dominance in the 20th century space race with Sputnik and Yuri Gagarin. It could shift the balance of technological prestige, giving China the upper hand in shaping the rules of lunar governance, including the extraction and ownership of space resources. Moreover, a Chinese-led lunar presence could establish geopolitical influence in the new lunar economy, enabling China to control access to critical resources like helium-3, which is viewed as a potential future fuel for nuclear fusion. For the US, a Chinese lead could create strategic urgency. NASA and its partners, including the European Space Agency, Japan, and Canada, might need to accelerate timelines and increase funding to remain competitive. There are also potential military implications. While the Outer Space Treaty prohibits the placement of weapons of mass destruction in space, a lunar presence could provide strategic advantages in terms of satellite positioning, surveillance, and communication infrastructure. The Moon, once a symbol of universal human achievement, could become the next frontier of national competition. Experts like Brandon Weichert, author of Winning Space: How America Remains a Superpower, argue that the first trillionaire will be the individual or nation that successfully mines the Moon's minerals. He contends that China's investments in space infrastructure are aimed at securing this economic frontier before others can. Weichert also warns that China's disregard for international treaties, as evidenced by its history of violations, could lead to unilateral actions in space that undermine global norms and stability. In response to China's advancements, the United States has initiated the Artemis program, aiming to return astronauts to the Moon by 2026 and establish a sustainable human presence. However, challenges such as funding constraints and technical hurdles have caused delays, potentially allowing China to surpass the US in establishing a lunar foothold. The competition has prompted both nations to form international alliances, with the US promoting the Artemis Accords and China collaborating with countries like Russia, South Africa, and Pakistan. The militarization of space further complicates the situation. China's 2007 anti-satellite missile test, which created a significant amount of space debris, demonstrated its willingness to develop and test space-based military capabilities. Such actions raise concerns about the potential for conflict in space, especially if China were to deploy weapons systems on the Moon or in cislunar space. The strategic advantage of high ground positions in space could be exploited to disrupt or disable other nations' satellites, communications, and surveillance systems. But wait, there's more from where that came. Neil deGrasse. Tyson's perspective. Neil deGrasse. Tyson has consistently observed that China's methodical and successful advancements in space, such as placing taikonauts into orbit and constructing a space station, demonstrate their commitment to becoming a dominant spacefaring nation. Tyson remarked, "China has met good on every one of their promises, urging the US to take China's lunar aspirations seriously." This perspective is rooted in the historical context of the Cold War, where the US was propelled to the Moon in part due to the perceived threat from the Soviet Union. Tyson suggests that a similar dynamic is unfolding with China. The scientific endeavors of China, particularly their robotic lunar missions, have opened new frontiers in understanding the Moon's history and its relationship with Earth. Tyson has acknowledged the significance of these missions, noting that they contribute valuable data that can reshape our comprehension of the solar system's past. For instance, China's Chang'e missions have provided insights into the Moon's geology, including the discovery of new rock types and the analysis of lunar mantle materials. These findings not only enhance our knowledge of the Moon, but also offer clues about Earth's own geological history. Tyson has also addressed the legal and ethical considerations of lunar exploration. He referenced the 1967 Outer Space Treaty, which stipulates that no nation can claim sovereignty over celestial bodies, emphasizing that space exploration should benefit all humanity. However, he expressed concerns about the potential for geopolitical tensions if countries, like China, proceed with lunar activities outside of international agreements such as the Artemis Accords. Tyson warned, "If we're capable of that level of peace in space, why haven't we shown that?" The implications of China's lunar exploration efforts are profound for the United States. Tyson has pointed out that the US must recognize the strategic importance of space to maintain its leadership and influence. He argued that space exploration drives technological innovation, economic growth, and national pride. The advancements made during the Apollo era, for example, had far-reaching effects beyond space science, spurring developments in various industries and inspiring generations. Tyson contends that a renewed commitment to space exploration could yield similar benefits today. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.